Okay, so until they join, I will introduce myself. So I am Suraj Borate. I am Nptel TA for Introduction to Robotics course from IIT Gandhinagar. And what we do in these sessions is that we solve previous year assignment questions that hopefully are helpful in the current assignment, which are very similar. So okay, so let's start. So this assignment is pretty much very similar to what we were seeing earlier. Uh, Very much formula oriented and few conceptual questions. Okay. So the first question is, so are you able to see the font size clearly, Anirudh?
Yes, yes, it's
Okay.
visible.
So the angular interval over which the waveform of your induced EMF in a BLDC motor remains flat top over a cycle. Okay. And the assumption is that the rotor is rotated at a constant speed. Okay. So when there's a flat top, it means that okay, this is the diagram for the EMF with respect to our time, and you can see that these are the uh, what we say, the different phases. Okay, and we have been asked for how much time the EMF is going to remain flat top. Okay, for a
Right.
particular this thing. So can anyone answer this? Like the logic answer is visible, of course, but what is the logic?
Actually, the duration for which the switch remains off, we'll have to calculate that. So initial angle is 30 to 150 degrees. It is remains switched off plus the duration for which the additional time period the first switch remains off. We add and subtract, and we get 240.
Yeah. So if you see visibly also the flat topped portion, if you see this for any one phase, okay, and see this region, if you calculate the how much angle it is. Okay, so let's say how much it will be. 150 minus 30 is 120. Okay, 120. So 120 plus 120 is 240. Okay. Another key point here is that it is important to make this assumption. Okay, that it is rotated at constant speed, because if it is not rotating at constant speed, what will happen is that as the speed increases, the frequency increases. Okay, so when the frequency will increase, what will happen? That this cycles will happen faster, right? And so what will happen at smaller degrees? Okay, you will get the flat top portion, because this will shrink, right? If let's say the speed
Yes.
increases by twice, then there will be four peaks in the same amount of time, right? So that way, in a cycle, then it will be half. The angular interval will become half. So that is why the speed should remain constant, and then you can say this statement. If it was directly asked, then the answer would have been different. Okay. So second question is, among the following statement made about geometry of the BLDC motor, pick out the wrong one. Okay, so if you see the BLDC motor, so what is the difference between BLDC motor and the DC motor? Is that in DC motor we require something called as brushes, right? And here we are saying it is brushless. Okay, so why we required brushes was that our rotating part, right? The rotating part had the armature, what do you say, the winding. Okay, the winding was present on the rotating part. So if the winding is present on the rotating part, then we cannot directly attach wires and provide the current to the rotating part, right? So we need to have some specialized arrangement so that the rotating part can rotate without entangling, right? And the current is provided to it. So that is why we required brushes. So now in BLDC, the innovation that is done is that on the rotated part we put the permanent magnet. So if the rotated part, if we put the permanent magnet, then we don't require the brushes at all, right? Because then there are no wires right over there. You
Right.
understand the concept? Okay. So that is the key difference. Okay. Now we go here. So rotor of BLDC accepts DC voltage, input voltage. Wrong, right? It is because now we have magnets. We don't have the coil only. So there is no question of input voltage. Okay. Stator of BLDC motor houses a magnet. That is wrong. Okay. It is the rotor that houses the magnet and stator has the coils. Okay. So it is ulta. DC motor and BLDC motor is ulta. So
Right.
the field generated in BLDC motor is rotating along the rotor. Okay.
Yes, it
So
does.
that is a correct answer. Why? Because
The magnet is on the rotor itself. It
yeah.
creates
So
the field
yeah.
beneath. So
So this is the correct answer. Armature conductors are powered without the need of brushes. That is what we
this is
discussed.
obvious.
Yeah. So let's move on to the next question. So is okay. Multiple people wants to join. Okay.
Just one request, sir.
Yes.
Post this call after you're explaining the entire questions. I
Yes.
have a few concepts and formulas to discuss. Would that be okay? Not
Yeah. Yeah. Fine.
problems, just a few
Hmm.
formulas, just for my
Okay.
understanding.
Okay. Okay. Okay, I will try my best to answer those questions. Okay. Okay, so recent now some people have joined. So for their benefit, I will just quickly go through the two questions because we have covered only two questions. Okay. Okay. So in the first question, I will just go through fast. It was asked like for how much amount of uh, portion of the cycle, okay, or the angular interval, the BLDC motor EMF will remain flat topped. Okay, so if you look at this diagram that has been thoroughly discussed in the class, so between 30 and 150 degree, you have 120 degrees and then you have 120 degrees, so it is the 240-degree. Okay, and the key assumption here is that the rotor speed is constant. Okay, if the speed is high, then let's say it's doubled or like increases, then what will happen? This cycle will shrink. Okay, so you will have more in the same period of time, you will fit in more cycles, and so the angular interval go on reducing. Okay, so it is important that the rotors at constant speed we are discussing this. Okay, in the next question that we discussed, it was asked that, okay, what is the wrong statement? So the first statement is the rotor of a BLDC motor accepts DC input voltage without a brush. Okay, first of all, there are no brushes in brushless DC motor. That's why it's called brushless. And the reason for that was that in DC motor, why we needed brushes? We needed brushes because the rotor was rotating and the rotor housed the coils. Now the coils cannot, we cannot attach wires to the coil and then rotate. Otherwise, the wire will become what we say, it will get twisted and get entangled, right? So we had a special arrangement called commutator, and which had the commutator brush assembly, right? But now what the idea is that on the rotor we put the permanent magnet and on the stator we put the coils. Okay, so we don't require the brushes, right? So the first answer is wrong. Second answer, the stator of the BLDC motor houses a magnet. Of course, so on the stator we had the coils and on the rotor we had the magnet. So this is a false statement. The field generated at the BLDC motor is rotating along the rotor, of course, because there are the magnets are on the rotor, so the field will rotate along the rotor. Okay, and the armatures are powered without the need of brushes. That's what we discussed. So the two questions we have till now discussed. Okay, let's move on to the third question. Okay, so here they are asking the magnitude of the flat portion and the frequency of the induced EMF in the BLDC motor while the rotor rotates at a certain speed are E1 and F1. If the speed of the rotation is doubled, then the magnitude of the flat portion and the frequency of the induced EMF becomes what? Okay, so the induced EMF is directly proportional to the frequency. Okay, and even the frequency is directly proportional to the angular. Sorry, this is the angular speed, and okay, and if you consider these two relations, okay, if you consider these two relations, the answer is obvious. Okay, so if the speed is doubled, then this will be happening. Okay, so uh, if I want to make some more statement about it, then the intuition behind this lies in the uh, the flux, the rate of change of flux. Okay, the rate of change of flux. Okay, so d phi by dt. Okay, it was something called as the induced EMF, right? If you remember, what law was this? Anyone? A direct proportional. Sorry. Anyone?
Related with duty, with duty ratio.
No, no, no. This is something we learned in 11, 12 standard, right? So the rate of change of flux is directly proportional to the induced EMF. Okay.
Inductance.
Yeah, in inductance we saw, but I am asking, is this the Lenz's law?
Okay.
I will
Actually, it
just,
was
I will just,
12 years ago. It was 12 years ago, so that's why
okay.
slightly foggy memory. Yeah, I think
Yes.
it was related with that.
Yeah, yeah. So that is the Lenz's law. Okay, the EMF induced in a coil is proportional to the rate of change of magnetic field. Okay, and now we need to understand then what is causing the rate of change of magnetic field. Okay, okay. So, so this is nothing but rate of change of magnetic field. Okay, and what causes the rate of change of magnetic field? It is nothing but the angular speed. Okay, is the angular speed that is directly changing the magnetic field. So that is the logic behind this. Okay, E is directly proportional to omega. Okay, and what is the logic behind F is directly proportional to omega? That is what we saw in the first diagram. Okay, so what happens is if your omega increases, okay, then obviously what will happen that the 60 degree what you see here, okay, will appear faster. Okay, and so if 60 degree will come much before, then obviously the frequency or the total cycle time is reducing. If the cycle time is reducing, the frequency is increasing. Okay, so that is the intuition. Okay, so this is the answer. Let's go on to the next question. So this, if you see this question, fourth question, uh, okay, let's try to solve this. Okay, so what all things we have been given, RA is given as 0.6 ohm. Okay, EB is given as 0.2. Okay, here omega. So you can see here, here also EB is directly proportional to omega. Okay, then DC voltage to the inverter is given as 100 volt. Okay, so the input voltage is 100 volt. So we also use this symbol in the DC motor section, and in every 60-degree interval the respective active switches of the inverter are operated on the duty ratio of 0.75. Okay, so the duty ratio D is equal to 0.75 and omega is equal to 60 radian per second. Determine the average value of the armature current. Okay. Okay, so this is the problem, okay, given to us. So any ideas on how to proceed?
So we know the edge bridge concept of VA divided by VG. We'll have to use that approach.
Okay,
A
and why
back
do we want to use H bridge over here? Any any particular reason?
actually actually the Hall switching mechanisms resembles edge bridge.
Yes, yes, very good.
So right.
So yeah, so if I draw this, okay, I haven't put the diagram, so let me draw. Okay, let me draw it in different color. Okay, yeah, so you are talking about this. So the numbering is usually like this. Okay, okay, so now what to do? You are saying that you can use this formula VA by VG is equal to 2D minus 1, right? The H bridge formula.
Yes. Yes.
Okay,
Yes.
so why can we use this formula here? So there are six switches now, not four switches.
So we have the duty ratio value given. So that way we can do the back calculation and solve for IA.
Okay, so let's see. They mentioned 60-degree, right? 60-degree. So at 60-degree, what is the situation? There are two. Okay, red one is on. Okay, and the yellow one is on in the opposite direction. Okay, and what about the blue? Blue is off, right? Can you see that? Is it visible? Okay,
Yes,
so
sir.
yeah, so ideally, see why the thing is at least one of the switches will be off. Okay, that you can see. Okay, and so that is why you since there are only four switches remaining, it essentially is an edge bridge. Okay, so that is the reason. Okay, if all the six were doing something in some other fashion, then we may not have been be able to apply this formula, but only since only four switches are being currently used, it is actually assembling this. Okay, so one of the legs, okay, is inactive. Okay, so let's Let's apply this formula. What will come? VA, what is the value of VA that we are getting? We know VG, right? It is 100 2 into 0.75 minus 1. So what is the value of VA? Is 50, right? 50 volt. Why? Because it's 1.5 minus 1, 0.5, 100 into 0.5, 50 volt. Okay. So we have VA now. Now what we want? We want IA. So do we know any relation between VA and IA?
Yes, sir. The back EMF formula.
Yeah. So can you tell what was the back EMF formula? VA is equal to E
E minus I by I minus IR.
E
E minus
minus.
IR. IA then RA.
Okay. So you are saying this.
Yeah.
Okay. So if we see how we got this formula, you remember?
Back EMF is equal to VA plus IRA. From that, changing subject of formula.
Okay. So we had something called as this resistance. Okay. And then we have the I going through it in the motor. Okay. In EB. The armature current. So if you see this formula, okay, what is the difference over here? So when they say that okay, resistance of each phase winding of BLDC motor is zero point 0.6 ohm, okay, and the input voltage is 100 volt, okay, so that is fine, that is VG, okay, but when they are saying okay, each phase there are two phases, okay, so now there are zero point 0.6 and zero point 0.6, two resistances are there, okay, and in each phase, okay, there will be a contribution from the back EMF, right? Hello, can you hear me?
Yes, yes, sir. You're audible.
Yeah, so we will have to kind of modify this formula, okay, so now we write this as VA is equal to 2 times EB into 2 times IA RA, okay. uh, Now can you calculate the value of what is unknown over here, IA, based on this formula? RA is given, IA is not known, EB we know, right? zero point 0.2 into omega. So what is omega? 60. Okay, so EB is equal to zero point 0.2 into 60. Okay, give me the value of IA.
EB is coming as 12 volt, and then using that VA will calculate.
VA we have already calculated, right? 50 volt.
Yeah, I'm sorry. IA we will calculate.
Yeah, yeah. So give me the value. What is the IA?
Also, sir, I think we're missing something a bit crucial. There are two switches. So there will be a factor of 2 for the back EMF, I guess.
So I have actually written 2, right? 2 into EB.
Yes.
Yeah. So 2 into IRA is also there. Okay. Why? Because there are two resistances.
Right. So
Okay.
the solution would be like 50 is equal to 24 time plus 2 times zero point 0.6, that is the resistance, into IA, since IA is unknown. And
Okay.
doing the reverse calculation, we get as uh, 20, 21.67 amperes.
Are you sure you are getting this with this formula? Because let me check. Okay. What is VA 50 plus 2 into RA is 0.6.
So I
Point.
made a small mistake. It will be V is equal to EMF plus current times resistance, not minus.
So what about others? What do you think? It is minus or plus?
Sir, it should be minus. Minus it should be. VA is equal to, because EB is the whole voltage and VA is the actual voltage. So internal resistance drop, we should neglect it. So it should be minus.
It should be minus. Why? Because EB is the back.
Uh,
EB is the back EMF, right?
yes, sir.
So EB is the back EMF. I into RA is what? The winding drop in the voltage.
Yes, winding drop.
Yeah. So what I am asking is the voltage that we provide to the motor. Okay. EB will be of opposite direction or the same direction?
Opposite.
Opposite direction. And IA RA drop will be the same direction or the opposite direction?
Same direction.
Same direction. Okay. So I think this VA, what we had, this diagram that we used to draw. Okay, so this was VG, and there was this motor. Okay, this motor has both your winding and the resistance. Okay, and then we used to say that this is the total voltage is VA. Okay, so this VA, no space. Okay, give me a second. Okay, so okay, so if this is the voltage given, okay, so you will get IARA minus EB ideally. Okay, now since here you have two windings, we are saying we multiply by 2. Okay, now even this with this formula, okay, I am not sure how we will get the answer that is given over there. Okay, because what, like what Anirudh is saying, okay, if this is plus then you get the right answer. Okay, but when this is minus, okay, you are not getting the right answer. Okay, so let me just calculate what is the answer according to our logic for now. Okay, so if this is 100, 2 into IA into zero point 0.6 plus EB we calculate as 12 volt, sorry, minus. Okay, so this is 112 divided by 2 into zero point 0.6. So what is the IA that we are getting? Anyone? you get 61 divided by 0.6, so 61 by 6 to 10, something like that. So that is approximately 100 amps. Okay, but the answer that is given is IA plus EB, IA RA plus EB. Okay, so if you use this formula, you will get the right answer. Okay, but I am not very sure about this formula. Okay, I am missing something, or ideally it should be in this way. Okay, uh, okay, so let's move on to the next question. Okay, so, but you understood, right? What you got EB, how to calculate, you know how to calculate VA. Okay, now the thing is, in this particular formula, why there is a plus sign over here, that is not clear. Okay, but if you use the plus sign, you get the right answer. Okay, logically I feel that there should be a minus sign over here. Okay, Anirudh or anyone has some other insight, then please share. Hello.
No, sir, I don't have any insight. It would be plus, I believe.
Okay, but you don't know why it should be plus, right?
Yeah, I mean, I was following the previous lectures, and on it, the back EMF formula where you are, um, deducting the armature resistance.
Mm-hmm.
So I use that approach.
Okay, okay, okay. So for now, you can follow the plus sign, but why plus sign? Okay, that I will tell you in the next lecture. Okay, I will try to find out that. Okay, because when applying formulas, we should know from why also, not just the formula. Okay, so so let's move on to the next question. Okay. For an inverter driving a BLDC motor, there are two switches active in every 60-degree angular interval of the rotor position. Okay, so if you see at like just observe this diagram, okay, or the previous diagram where it is more clear, then you can see that. Okay, so if at every 60 degrees interval, you will always have some two switches active. Okay, so it just this diagram is very important. You keep this in your mind. Okay, because most of the questions are going to come from this diagram. Okay, the switching instance of each switch is completely decided based on the Hall switch information. So if you see, look at the Hall switch information, it is not, it is not invertible. If you see this, okay, if you have this graph, let's say, where is the Hall switch graph? Okay, so this is the Hall switch graph. If you see from this particular region, okay, can you determine where exactly or what is the current situation, because it looks very similar, right? This entire region is the, it looks uniform. Okay, while the motor rotates from here to here, it's completely uniform. From here to here again, it's uniform. So it is in phases only at the, the edges, something is changing. Okay, so the output state, what was that, this thing, switching instance of each switch is completely decided based on Hall switch information. So it is not true. Okay, it is actually, it is reverse. Okay, so it is the switching instance that generates this information. Okay, also by just looking at the Hall switch information, you cannot directly conclude anything. Okay, you need to understand what is, you need more knowledge. Okay, so there will be one leg with both switches turned off at any given instant. This we have already discussed. Okay, so if you look at here, only two of them are on, but the blue is off. Okay, so, and like that you will always see each switch conducts for a total angular duration of 120 degrees. Okay, uh, so this everything is from the diagram. So, okay, so from the following statement, okay, again the same question. Okay, so if you see the output of each switch alternates between high and low for every 180 degrees. Can you see that? If you see this is 180 degrees. Okay, where is it? See this, right? So from 0 to 0 in 180 degrees. So so basically there are these questions will come. You just have to be observant. Okay, so the output state of a Hall switch depends not only on the rotor position but also on the direct rotation of the rotor. Okay, so direction of the rotation of the rotor. Okay, so what do you think about this? Direction of the rotation of the rotor. So do you have the
No,
direction
it's
information?
incorrect.
Huh?
It's incorrect. Actually, output state has nothing to do with the rotor direction.
Yeah, but
Output.
why is it incorrect? The answer is visible, but what is the reason for that?
No, no.
Okay, so
The reason is actually um, rotor position direction. Rotor position is in a brushless DC motor is basically influenced by the magnetic field.
hmm,
So the position of the switch or the state of the switch doesn't actually decide where the rotor should be positioned. It can only dictate how much current and voltage would be
okay,
there.
so yeah. So to put it in simple words, okay, so this information that you are seeing, Hall effect information, okay, this is just showing the position of the switch, so position of the rotor with and how it is related to the switching of the coils. Okay, so it has nothing to do, and so you will get you will get a high EMF when there is high like flux matching. Okay, so between the coils and the magnet. Okay, so it has directly do with the position of the rotor and not the speed or the sorry, not the direction of the motion of the rotor. Okay, so if at that position it might be rotating any direction, the flux engagement is the same. Okay, so that is why this is the answer. Every Hall switch output completely determines the active zone of a switches in one respective leg. This we have already answered. Okay, in here, where did we answer that? The switching instant of each switch is completely decided based on Hall switch information. Okay, so this we have already said that just based on the Hall one of the switch we cannot tell anything. Okay, uh, okay, so these two are incorrect. Okay, seventh question. Okay, the rotor of BLDC motor rotates at a speed of 1200 rpm. The rotor has 4 poles. Okay, the frequency of the output pulses from each Hall effect switch is what? Okay, so what is the way to deal with this? So there is this formula. Okay, here F is equal to 120 into F divided by P. Okay, where P is the number of poles. Okay, and here uh, sorry, omega. Okay, and where omega is in the rpm. Okay, so if you apply this formula, what you will get? 120 into F divided by 4 is equal to 1200. Okay, so we can say this is 10 and F is equal to 40 hertz. Okay, So can anyone tell me again the same question I'm asking? How did we get this? Okay. So from your assignment point of view, this is not important, the derivation of these formulas or any of these formulas, but it is very important that we understand this. Okay. So you can look it up. Okay, the derivation, or we can discuss in the next class. Okay, but it is very important to know that this number of poles is a very important factor when we are choosing a BLDC motor. Okay, so when we choose a BLDC motor for our application, let's say we want to fly a drone or something like that. Okay, there are two types of BLDC motor. So one is in runner and out runner. Okay, so the in runner motor has the rotor inside and out runner has the rotor outside. Okay, and in the in runner type, let's say if this is the in runner type and we have the rotor here and we have the coils outside. Okay, the height of the motor, okay, and the diameter of the motor is enough for us to tell whether the motor is a high torque motor or high speed motor or something like that. Okay, so you might have seen that there are a lot of flat motors like this. Okay, so these motors have high a larger diameter. Okay, so when there is a larger diameter, you can fit more number of poles into it. Okay, and so since there are larger number of poles, what happens is you can get a lower RPM. Okay, and the consequence of getting a lower RPM is that the power is nothing but torque into omega. Okay, and so if the for the same amount of power, if the RPM is low, we get high torque. Okay, so if you see the modern robotic arms, okay, why we call modern is because BLDC motor is a very important motor in today's robotics. Okay, if you see the currently the cheetah robot, okay, the Boston Dynamics, all the robots, that awesome robots that do backflips and all, okay, they all use BLDC motors. Okay, on drones also we use BLDC motors, but those motors are not flat motors. Okay, those motors are taller motors where the height is more and width is less. Whereas in the quadruped robots that resemble legged robots, okay, like Boston Dynamics dog and all, there they use flat motors. Okay, why? Because the number of poles is higher. If number of poles is higher, omega is low. If omega is low, torque is high, and for such motors we need high torque. Okay, because it has to lift the entire weight of the robot and walk and jump and all this stuff. Okay, so high torque is required. Okay, and one of the good things about this motor is that BLDC motors can are an essential component in building something called as back drivable actuators. Okay, so remember these words. These are very important words when you start designing your own robots. Okay, so what is back drivable actuators? It means that when there is some disturbance at the load side, okay, you are able to move the motor backwards. Okay, otherwise what happens in a motor like a DC motor, okay, there is a gearbox that comes at the ahead. Okay, and this gearbox has a lot of friction in it. Okay, and so this friction doesn't allow the motor to move back instantaneously. Okay, right. So whereas in drones, what happens? This is not flat. This smaller. This is like the diameter is less. If the diameter is less, what happens? The number of poles is less. If the number of poles is less, what will happen? By this formula is important. What will happen? If the number of poles is less, the speed will be high, and that is what we want. Why? Because the thrust produced by the drone is directly proportional to the speed of rotation of the motor. Okay, so this is why this formula is very important. Okay, this is just a question in your assignment, but it has high implications. Okay, so let's move on to the next question. Okay, so everyone got how you got the 40, right? You don't forget that. Okay, in all this story, extra story. Okay, so in comparison to a forward rotation, in the reverse rotation operation of BLDC motor, the magnitude of induced EMF would be different, but polarity is the same. Okay, and for a given speed and range of rotor. Okay, so what happens to the first this thing? Why will the magnitude be different? There is no reason, right? We know it is directly proportional to speed, right? So the magnitude should be same. Okay, so that is what our next option is saying. Okay, the magnitude of induced EMF is the same. Okay, but polarity is different. Why? Because as we have discussed by Lenz's law. So I would advise that you go you when you whenever you get time, Lenz's law, Faraday's law, okay, Biot-Savart law, all these laws that we learned in electromagnetics. Okay, you just revise. Everything comes from that only. Then whenever you are even when you are memorizing a formula, something goes wrong, you will understand. Okay, so okay, the frequency. Okay, this question is right. Okay, the switching logic for the operating inverter switches in BLDC motor drive cannot be employed. What is PMSM? Permanent magnet synchronous motor. Okay, true. Though the inverter topology remains the same, this is because of what? First of all, what is the question? It says that whatever you do in BLDC motor, okay, this switching logic that you had, okay, is not applicable for PMSM. Okay, and what is the reason for that? So what exactly is a PMSM motor? What is the main difference between BLDC and PMSM? Anyone? It looks completely like a BLDC motor, right? Whatever the construction and all. So what is the difference?
A fixed magnetic field. The magnetic field between PSM is in synchronous with the current flow, whereas in BLDC it is not.
Okay, and how do you get that synchronization?
By polarity switching.
Yeah, so here what we do is we have a way to smoothly change the polarity, not by just by switching. Okay, so it's like you get a sine wave kind of waveform for each phase. Okay, and you have these waveforms at some phase angle. Okay, so that is the main difference, and as a result what happens is that PMSM kind of motor, okay, these motors have a higher efficiency. Okay, and they are costlier also. So main difference is their controls only. Okay. Um okay. So this is the answer. If you see the other answers, it has they are saying BLDC can be operated with a unipolar voltage across each phase, since back EMS are flawed while PMSM needs a bipolar. Okay, so these are not the main reasons. It's just the it requires PMSM requires the sinusoidal current flow. Okay, whereas the BLDC requires the DC current. This thing. Okay, why? Okay, so very important is that this is interesting. So okay, so in BLDC, when we say is BLDC an AC motor or a DC motor?
LDC is a DC motor.
Someone else can answer. Anyone? Is BLDC a AC motor or DC motor?
DC.
Okay. So if it was DC, I wouldn't have asked the question itself, right? So it is actually an AC motor. Okay. There are three phases. Okay. In each phase, also. So what is the definition of DC? DC current. Huh? DC means
Oh,
what?
I see. Since the current is generated through a magnetic field, it's alternating current. That's the assumption.
Yeah. The thing is there are three phases. Okay. It is not a single phase, and in each phase the current is actually switching, right? Like this. Okay. It is an alternating current, and there are three phases. So you cannot have just plus or minus, okay, and connect to the motor. Actually there are three wires first of all that comes out of the motor. There is no two wire. In DC motor you had only two wires, plus minus you give, you will get it. Okay. Now you cannot give here plus minus also. Why? Because then it is required that this becomes minus sometimes and this becomes plus sometimes. Okay. So it is alternating. The polarity is alternating. You cannot have plus always over here, minus always over here. Okay, otherwise the motor will not run only. And this is what I am saying for the one direction motion of the motor, not like in here also you do this minus plus, but when you do, the motor will rotate in opposite direction. Okay, here just for one direction motion also you need to alternate. Okay, so this is an AC motor, not a DC motor. Okay, the name is very confusing, but it is an AC motor. And you can see this in the first lecture of the motors, when the motors professor came and he started, right, he gave a chart of classification of motors. In that you can see BLDC comes in the AC motors type, not the DC motor. Okay, so I have discussed all the questions. I will discuss that plus sign and minus sign in the next lecture again. But for now, if you are getting the right answer to the plus sign, I would recommend plus sign. But I would say that you should try to find out the reason for that. Okay. Uh, any doubts you wanted to discuss some formula or something like that? Formula?
Yes, yes. Just could you explain to us the concept of ripple torque? Is there any specific way to derive this value?
Okay, so ripple torque, you can get a question like, whether the torque is directly proportional. Okay, the ripple torque increases or decreases or something like that. Okay,
Uh, Okay.
that kind of question you will get, like whether the if there is a ripple, if you increase the angular speed, what
Mhm.
happens to the ripple torque? Something like that can come. Okay, so if you see ripple torque, so that is like BILR, something like that. Not the ripple torque, the torque itself is BILR something. Okay, so what I think is that if you have I over here,
Mhm.
okay, that will also be impacted by the uh, the same frequency. Okay, this frequency only. Okay, because the voltage and I will have the same frequency in it. If there is some sign component in that, then it will also affect the I. If voltage has the sign component, then also I will be affected by it. Okay, or there is some what we say, not the sign component, but whatever switching is happening over here in the voltage. Okay, you will get a similar pattern with a similar frequency in I. It may be shifted because we have some EB and all that stuff over going on. Okay, that's but if you have some switching over here, okay, you will get the similar switching over here and similar switching over here. You cannot have a different frequency of this and here and different frequency. That won't happen. Okay, because this is that same I coming over here. Okay, what will happen is the same frequency will be carried over to the torque.
Okay.
Okay, and so
So
that is why what happens is the if the omega increases, the frequency increases. Okay, and what will happen is that delta t, in the delta t region, it is a
mhm.
function of some. Okay, so you are talking about ripple torque or the frequency of ripple torque. These are two different things. Okay, the frequency of ripple torque will increase.
Okay, frequency of ripple talk to be precise, actually.
Yeah, so the frequency of ripple torque will increase by this logic. Okay, why? Because if this frequency is increasing. Okay,
Hmm.
so the frequency of ripple torque will increase because this torque is on this side. Okay, so that is the intuitive this thing. I don't
Okay.
know direct formula for this. Okay, but if they ask something like the magnitude of ripple torque, okay,
Right.
then that will come from delta I. Like we had, in one of the previous sessions, we calculated the delta I.
Yes,
Yeah,
duty ratio was given VA
yeah,
VG
yeah.
divided
So
by
you
duty
have to
ratio.
use that formula, and then you can conclude. Okay.
Got it.
Mhm.
Got it. Thank you, sir. I've had my doubts cleared.
Okay. Anyone else
The
has something?
rest of them I've left, actually, sir.
Okay. I cannot see all the screens. So okay. Thank you. Uh, we'll meet next time.
Sure. I request you to upload this recording right away, sir. Not till Wednesday,
Okay.
so
Okay.
that I
Yeah.
can.
Yeah. I will upload. Okay. Thank you.
Thank you.
So are you able to see in the recording? Usually, what happens is the size of the font is less, right?
No, no, that I can adjust. I can zoom in on the
Okay.
video
Okay.
itself.
Okay. Fine.
But if the
Th-
video is there, that is helpful. Actually, I can recapitulate some concepts that I missed during solution of the questions.
okay. 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 Sure. I will do that. Okay.
Thank
Thank
you,
you.
sir.